So up next, we have Dan and Wes from DCP. They will be introducing you to the world of distributed computing. They'll present a short presentation on what distributed computing is and how you can leverage it for the hackathon. And we'll also do a demo. So Dan and Wes, take it away.
Awesome. Thank you so much, Manushi. Just before we get started with the workshop, we're actually going to just talk about the DCP challenge. So I know a lot of people have been wondering what challenges they can work on. So now's a perfect chance to see what custom challenge there is. Give me 1 second to pull up my. Awesome. Hopefully people can see my screen. Let me know if you can't. Okay. I'm not seeing any messages contrary to me sharing. So for the DCP challenge, the challenge is, what would you build with a personal distributed supercomputer at your fingertips? So the purpose of this challenge is to just be able to get you delving into distributed computing and also just to see who has the best application of DCP. So the prizes are, for the first place, 750 CAD dollars per team, and for second place, 250 CAD per team. Along with those cash prizes, you also get a coffee chat with Dan, the CEO, or the CTO, and mentorship plus credits to continue the project. So we want this to be more of a long-term project for you to get hands-on experience. And everyone will be able to get a DCP certified badge, and along with that, learn some new in-demand skills and also try something new, and potentially even get a job. So under your toolkit, you will have exclusive deployment access to the platform and get 25 credits automatically when you sign up. And you also will have access to getting started and troubleshooting guides available on Discord, along with mentorship support. So if you need any help throughout the hackathon or after this workshop, feel free to message the DCP team on the sponsor channel on Discord. And along with that, we'll have a great workshop taking place after I finish speaking and an opportunity for Q&A. Good luck. And with that, I'd like to hand it off to Dan and Wes.
Hello, folks. I'm trying to start my camera, but it says the host has stopped it.
Okay. I think you should be able to.
I'll try again. Oh, looks like that works. Hi, everyone. I'm small on the side. I think TOHacks team is has been pinned. I don't know if it's possible to switch the video over to. All right, guys, nice to meet you. Disregard this creepy looking mustache. I'm just, not taking myself too seriously and having fun here with different hairstyles and everything else. But my name's Dan, background not in business, but in physics. And so that would be my answer to the challenge of what would you do if you had a distributed supercomputer at your fingertips? I would solve Maxwell's equations for all kinds of really cool geometries to allow magnetically levitated hyperloops. And that's actually some of my research that I was doing 3 years ago. And I couldn't come up with enough compute power in order to solve things in a reasonable amount of time. So fast forward 4 years, and this is our hack, is this platform that takes code and allows it to execute across many machines simultaneously so that it finishes faster. We made a go of it. We made a little company called King's Distributed Systems. It monetizes or commercializes that software with enterprise and industry. But we also made this entity called Distributed Compute Labs. It's an educational nonprofit, and its mission, along with the rest of us who are leading this, we're scientists, not business people leading this. We're giving the platform away for free to academic institutions worldwide. We have a footprint right now in Kenya, starting in Nigeria, Nepal, Canada, obviously, and we're trying to break into the States. They're a little bit trickier because America first, right? I say that with affection. Anyway, so yes, DCP, the Distributed Compute Protocol. It sounds like TCP/IP for a reason. We're trying to become, over time, the web standard for distributed compute. The internet moves around data. We want to move around compute and take advantage of every last CPU, GPU, FPGA, neuromorphic chip, quantum computer, and eventually, who knows what comes next. And why? Being a physicist and not a computer scientist, I am half as talented as probably the majority of you in terms of writing code, probably not even that good. So I need very easy computing tools to use. I want to be able to say, this is my input data or list of parameters that I want to feed to this equation. And this is my equation or my work function or the operation I want to perform over and over and over and over and over and over again for every single input element in that set. So what I'm describing to you sounds a little bit like a loop, right? A parallel loop, or one in which there's no recursive dependency. And that's what we've built. It's a framework to take an arbitrary input set, could be images, MP3s, random data, and then you declare an arbitrary work function, which could be like some sort of inference, machine learning, machine vision, natural language processing operation. And what it does is you just express those two things, which Wes will talk about. It just goes to the scheduler. It goes to every connected device, and each input element in the set gets spread out with the work function across all those computers. They all compute the results, send them back, stitch them in the right order, and give them back to you. You don't have to do instance type management, port forwarding, and configuration and version type, and this, none of that. It just works. Input set, work function, execute, and you get all your results back. So the reason we did that was to make non-computer scientists like me able to use a lot of compute power to answer questions faster. And there's another angle to this, which you're going to see today. We've actually superimposed a bank on top of all of this. Da, da, da. So in this world, we're actually measuring CPU seconds, GPU seconds, bytes in, bytes out, and a whole bunch of other little characteristics that have to do with computational workloads. And here's the catch. In the same way as in smart electrical grids, you can consume kilowatt hours from the grid, and you can also set up a solar panel and give or sell kilowatt hours back to an electrical grid. In our world, it's the same. You can do compute for the network by pulling down tasks, executing them, and then essentially collecting these compute credits. It's not a cryptocurrency. It's a measure of the amount of compute workload done. It could become a cryptocurrency, but let's not even go there right now. Similarly, when you deploy work to the network, you then supply these compute credits. So the end effect is people that participate in the network as much as they consume from it. It's net free. So it's a way of being digitally inclusive and allowing anybody to have access to massive compute power as long as they participate as much as they take. You give as much as you take. Some of the coolest projects we're doing right now, we're setting up compute clusters at Africa Nazarene University. So all of the computers on-prem, we can turn into a compute cluster that they can harness. Maybe a bit closer to home here in Canada, we did the same thing at Ryerson University. They have hundreds and hundreds and hundreds of computers doing literally nothing, especially right now in the COVID times where everyone is at home anyway. We stitched them together to make a compute cluster that students and researchers there can use. And we want to replicate this everywhere, and it's free. And you're wondering what's in it for us? Well, A, we're scientists, so we believe in STEM in the first place, but it's also hugely strategic. If we make a tool that's actually useful and cool and accelerates science, innovation, technology, and everything else, it gives us some credibility to then commercialize this with industry and enterprise. So it's kind of like a Robin Hood story where you take from the rich and give to the poor. Not saying that you guys are poor, but students that definitely have not millions of dollars to spend on AWS cloud computing like corporations do. So anyway, that's the dream. And then I could go beyond this and talking about like eventually we want like to really bridge the gap between non-scientists and scientists and so on and so forth, but I'll leave it there. What we're trying to do fundamentally this evening and this weekend and in future hackathons is really get feedback at the end of the day. So the reason we're doing these workshops, we're not selling anything, we're not pushing anything. We're actually asking people to try this and tell us how we can make it better. It's very limited in what it can do right now. It can do some things really well, but we have a roadmap and a vision and all this stuff to make this be able to do everything. But right now we're crawling before we're walking and running. So any amount of playing you do with this, any inspiration you have, any ideas are gold to us. So help us, and we promise we'll make it better. Here's an idea of an application that could be really cool. There is a library called TOHacks, which is essentially OCR, optical character recognition. You can feed it some scanned writing or whatnot, and it'll turn it into the actual character user selectable text. If you go to AWS right now, you can actually drag and drop a PDF file, and they'll charge you $1 per page to do that scan, OCR, and then document creation. $1 per page. So if you have a 200-page book, that's $200. But you could clone that GitHub repo, Tesseract.js, and you could probably whip up a DCP app that takes a PDF document and just splits off the different pages as slices of that input set I was talking about, and then applies the optical character recognition to each slice on different workers. And Wes will talk about like the worker client scheduler paradigm, and then stitches it back together again for pennies instead of dollars. So that's one application. Others are fractal rendering. It's perfectly parallel. Ray tracing is perfectly parallelizable. Monte Carlo simulations are perfectly parallelizable. Fourier transform. I mean, like I can go on and on and on about perfectly parallelizable problems. I'm sure you can as well. But or image analytics. Imagine if you had some drone footage, a drone just flying down the street in a city. It could actually map out the presence or not of cars parked on the side parking. Imagine if it created a Google Maps overlay to show where there was free parking versus no parking, like vacancy versus no vacancy. It's like that when you're driving somewhere, you could actually navigate to an available parking spot that's been made like sort of real time with machine vision, drones. Like, I mean, we're just putting everything together, right? Anyway, so I love like the ideation about what you can do with the compute to advance science and technology and business and everything else, but we can do that some other separate time. Right now, I'm hogging the precious airtime to actually show you, okay, well, how do you use this thing? And please try it, break it, tell us what can be made better, and we'll improve it. Caveat right now, you're actually catching us right in between our upgrade between our version 3 of our platform and our version 4. Our version 3 sucked in a way. It was awesome in another. It was the penultimate prototype, but it sucked. When I say it sucked, I say that affectionately in terms of its actual ability to scale. So whereas the previous version could handle about 1,000 people simultaneously connected, this next version will be able to handle about 100,000, 150,000. Now we're talking about an actual commercial scalable product. However, it went live yesterday. So we're still ironing out kinks and everything else. So it is quite possible that you will discover all of them. And so we ask you to be patient. Everything should be smooth by this weekend's hackathon. But I believe production is robust enough to demonstrate everything we want to demonstrate tonight and give people an advanced taste. And of course, if you're really interested in joining us in the long term, because we have an excellent relationship with students. I mean, it's our #1 source for talent. I don't believe in trying to pay like $300,000 a year for people who think they're better than everyone else. Students are the most talented, the most ambitious and eager, that you can find. So we're more than happy to bring on interns and folks, of your vintage. So anyway, with that, patience with our V4 brand spanking new rollout. And all feedback is super welcome. That's it for me. My name's Dan. I'm on LinkedIn. Happy to connect, happy to chat with everyone. I'll be hanging out, but I think now it's over to Wes. And Wes must unmute, and there he is.
Good afternoon, ladies and gentlemen. As Dan was saying, my name is Wes Garland. I'm the CTO of King's Distributed Systems. Very much like Dan, I'm experimenting with hairstyles right now. This one is called My Barber is Closed Because of the Pandemic, which is why I'm wearing a hat. Very interested to find out that Amazon is charging $1 a page for that PDF product. That's kind of crazy. So without further ado, I'm going to share my screen here. I've got a slide deck on the go that helps me talk a little bit. I'm going to talk about a little bit about DCP, a little bit about distributed computing, and away we go. And I'm going to keep an eye on the time so that hopefully we have time for some questions at the end. And by the way, if you've got questions in the middle, feel free to, I guess you can't shout out, but I'll try and check the chat every now and then. So without further ado, and I will post a share. Interesting. I will post a link to this slide deck in the chat at the end of the presentation so that you'll be able to reference it if and when you decide to build yourself some DCP applications. Okay. So today's talk is called Developing with DCP, Writing Client Applications for the Web. DCP runs on both, it runs on web technology, but it runs on both web browsers and runs in Node.js. This talk will actually cover both, but the focus is on the web end of things and how things work. There we go. Like I said, I'm the CTO here at King's. I've been writing software for an incredibly long time. I spent a couple decades in the telecom field. I'd done a lot of research in JavaScript server-side programming, in particular module systems, before I arrived here at King's. I'm a Unix systems developer, and that gives me the expertise to lead this team with respect to developing robust, scalable systems. I worked on things like the require command before it existed with Common JS, and I've built one complete JavaScript ecosystem to date. And now that DCP is really seeing the light of day, I guess that means 2, which is pretty cool. So what is DCP? So DCP stands for the Distributed Compute Protocol. And this is a protocol and a platform we've put together that is designed to make it both possible and easy for software developers to write applications that perform perfectly parallel algorithms. So if you have a perfectly parallel algorithm, you can probably express it in DCP today. Now, by perfectly parallel, what I mean is that you have a problem set with a series of steps that have to be solved, and that none of those steps depend on one another. For example, in mathematics, we have inductive proofs. And an inductive proof, the nth stage always depends on the nth minus 1 stage. And those types of problems are not suitable for, they're not perfectly parallel algorithms, so they're not suitable for the current state of DCP. But there's an awful lot of perfectly parallel stuff, especially when you start thinking about algorithms in the bigger picture. For example, OCR itself, optical character recognition, might not be a perfectly parallel algorithm. However, you can OCR 1,000 pages in parallel, with each page being an individual OCR operation. So when you start grouping your smaller serial operations, you can often discover parallelizable subsets within there. And this requires a little bit of new thinking for most people and some creativity, but we can really do some incredible things with DCP that are simply not possible on our current compute platforms. I've been at this long enough now that I've seen revolutionary technology introduced multiple times. And the one thing that has every one of those instances has had in common is that they weren't revolutionary necessarily on their face, but they were revolutionary in terms of the capability that they unlocked in other developers. So what really happens is a company brings out a cool toolkit, and if it is revolutionary, and I believe DCP most certainly is, people build incredible things out of it that the people that actually built the toolkits never even envisioned. So when Dan asks you, what would you build with your personal supercomputer? Man, I can't wait to find out because I know that some of you are going to build stuff that absolutely blows my mind. How does DCP work? Software developers have problems they need to solve. They solve them using JavaScript and DCP, and that runs in the browser or in Node.js. So what happens is basically they send jobs to the scheduler, and the scheduler returns their results. And our scheduler handles all of the figuring out who to send what jobs to and who can handle how much work and divvying it up and all this work and putting it all back together again and getting it to you. That's one of the great things about DCP, and it really underlines one of my core principles for software design, which is that the people using the software need to be concerned about what they want to do, not how the software works. So there's whenever I talk about DCP to a lot of other industry professionals, the first question is, why JavaScript? It doesn't seem like an obvious solution until you sit down and really think about it for a while. So part of that reason is simply I wouldn't be here if it wasn't JavaScript, because that's where my research interests lie. But the reason JavaScript was chosen has a lot to do with some of the very basic needs that this platform has. So one of the things that we want to do is we want to make it possible for you to run work on somebody else's computer. That somebody doesn't know you and they don't trust you. So we have to be able to take your work and put it on their computer and run it in a way that they're going to be confident that you're not going to be able to cause problems for them. And JavaScript is very trustworthy. Every one of us runs untrusted JavaScript every day. If any of you happen to be running, watching this webinar either in a rerun on YouTube or you're using the Zoom client in your browser right now, you're running a JavaScript program. Every time you Google and click on a website, you're running untrusted JavaScript. Well, assuming you don't trust the owner of the website, which is a really good attitude to take towards the world when it comes to computer security. JavaScript's really fast. It's the fastest interpreted language that I am aware of. There's always some language that's going to be faster at some little corner case, but JavaScript is absolutely incredible in terms of what it can actually do within the core language as an interpreter. And this is because we've had 4 companies, Mozilla, Apple, Microsoft, and Google, essentially racing to have the fastest JavaScript engine now for a decade. And they've poured millions and millions of research dollars into it, lots of really cool techniques for just-in-time compilation and a whole bunch of other things. And long story short, it's fantastic. If you compare JavaScript to any other interpreted language, it will come out on top. And when I say compare it to an interpreted language, I mean not calling out to libraries that are written in C. We've had results in JavaScript, generally compute bound, napkin math, they're coming out around 2C in terms of speed. I've actually been surprised and had some algorithms actually run faster in JavaScript than they have in C for me. And the reason is that the way the JavaScript JIT works happens to be very good. And it can see things in a sort of the dynamic runtimeness that sometimes statically optimizing compiler can't see. JavaScript is everywhere. It's ubiquitous. I look around my office right now. I see 1, 2, 3, 4, 5. I'm holding my phone if you can't see my picture. 6, my iPad. 6 machines that can all run JavaScript and all run it daily. I've seen JavaScript. I've actually seen DCP running on the dashboard of a Tesla car. I've seen it running on a phone. I've seen it running on a fridge. It's absolutely incredible. The language is everywhere. And the reason is that it's a piece of core web tech, and the world is extremely web-centric now, and I believe it will be forever in some future flavor of what the web is today. It's platform independent. So you can run the same JavaScript code on an ARM machine or on an Intel machine and get exactly the same results. And I mean exactly the same results, right down to the very last bit, if we're employing some of our very careful tricks in DCP. And this is really important because it helps us make sure in some regards that we're getting accurate answers because we can rerun them on multiple machines. And it also makes sure that when you're trying to stitch together for example, points on a curve, that you're not having minor differences between CPUs, math functions causing you unusual problems, or you're not having problems with, your rendering. If you're doing a huge ray trace, for example, your squares don't get slightly misaligned due to rounding errors between different machines. We don't have that problem here. JavaScript is also suitable as a compilation target. So other compilers actually emit JavaScript. We have WebAssembly, and we have a compiler called Emscripten, which actually takes LLVM bytecode, which is emitted by other compilers like the Clang C compilers, Julia, and so on and so forth, turns that into WASM, and it's actually possible to bring in workload from other languages that way. And that's particularly useful for bringing in specific types of libraries that are problem domain specific. This picture here just kind of shows the basic DCP overview. So we've got a scheduler up here, and that scheduler receives from the client. So these are the things running the application programs. They get like work functions and arguments and data, and it sends the results back to them. We have in the cloud, we have some processing that moves stuff around the network. We have some databases and some storage and whatnot. And then we have connections to all kinds of workers all around the world where we send them work. We send slow workers a little bit of work. We send fast workers a lot of work. And we put things together in the most efficient way we can to satisfy the needs of the whole network and ship the results back to the clients. So what is a DCP job? A job is an input set, a work function, and arguments. An input set is any enumerable data type in JavaScript. So typically they're arrays. And you can look at your data set in many ways if you're developing an enumeration method for it. For example, one way to enumerate or to iterate over a video would be one frame at a time. To iterate over a PDF might be one page at a time, and so on and so forth. So this is how we come up with input sets. The work functions each get one element of the input set and the arguments. And they return the result of applying that work function to that input set with those arguments. So essentially, it's a little automaton that takes a piece of input, runs the algorithm, and returns a piece of output. And arguments, they're just arbitrary values, just like arguments to any other kind of function in any other programming language that you're familiar with. So we have a client library called DCP client, and that's actually available on NPM right now. We just updated that with our version 4 code very recently. In fact, I just patched it this afternoon. So inside DCP client, there's a module called compute, and compute.for is the key function. So remember Dan talked about things that seemed like loops. I designed the API to seem like loops. So compute.for is named for the for loop. And what this API function does is it associates an input set with a work function and some arguments, and it returns a job handle. And then the job handle has an exec method, and this exec method sends the job to the scheduler, and it returns a promise. And when the promise resolves, it yields the output set. So I'm going to go through a quick HTML document example here, and in the next 5 minutes we're going to build a complete working pardon me DCP program. I'm just going to pop back here for a second. And okay, and so when we write a web document, every web document starts the same. We declare the document type, or at least you're supposed to. We have an HTML tag. We have a head section of the document, and in the head section of the document, we tell it what character set we're using. It's good practice. But importantly, we tell it to go fetch the DCP client script from our scheduler. So that URL there will always have the latest version of DCP client that matches the scheduler available on it. If you're using NPM with Node.js, you'll get the same file from npmjs.com, but Keep an eye on your code because you may need to update it from time to time. If your code is way too old, it'll actually tell you that it can't connect to the scheduler. And as long as you didn't download it last week, you're not going to have that problem right now. And of course, we have the body of the document, and we close our HTML tag. Now, we need to define a work function. And when I prepared the slide deck, I tried to think of what the simplest work function I could think of was. And the simplest programming function that I thought of that could be parallelized was turning a mixed case string into uppercase. Now, I realize that's a very boring example, and that's exactly the point. I don't want to talk about string character transformation. I want to talk about distributed compute. So work functions are executed on remote workers, and each call to the work function gets one element of the input set and returns the corresponding element of the output set. So in this case, each instance of the work function is going to receive a character from a string, and it's going to return that same character, but transformed to uppercase. There's a little gotcha with writing DCP functions. You have to make sure that your work function calls progress. If you don't call progress, your job will not run to completion. You also need to call progress every few seconds if you have a very computationally intensive job. If you don't, the scheduler may decide that you have entered an endless loop and terminate your job. So you want to make sure that you don't get into that little trap. For any of you that are interested in API design and are wondering why I insist on a minimum of one progress call, no matter how fast your work function is, this is part of where designing for humans comes into place. I had an interesting discussion not that long ago with another developer, and the thesis was essentially that APIs are interfaces to computers. And my take is that APIs are interfaces to other developers. And one of the things that, as an API designer, I need to make sure that you guys are aware of is this weird little trap with the progress function where your job could get terminated if you enter an endless loop. And the best way for me to make sure that you know about progress is to irritate you a little bit and make sure that you use it. Until progress is no longer necessary sometimes, it will be mandatory all the time. Your work function is stringified. In JavaScript, that just means we take the source code from the function and turn it into a string before we send it to the scheduler. You actually don't need to make your function be a function object in your code, but it's really convenient to do that because you get paren and brace matching help and so on and so forth from your editor when you're writing the function. But you need to be careful that you don't try using things like global variables or variables that your function closes over, because those don't survive the stringification and the transmission to the scheduler. So just make sure that your work function is all one piece. So the function that I've declared here, I called it work function, and it receives as its argument a letter. It calls the progress function because it has to, and then it returns that letter transformed to uppercase. That's it. The very simple work function. And again, the point is to show you guys how to distribute this rather than to do complicated work function-y things. So how do we actually get that work function deployed? We need to create an input set, and this is a web application. So I'm going to bind the variable input set to the array that I get from the value of a text box named input string. And then I'm going to declare a job handle, and I'm going to get it by running compute.for input set work function, and this associates those two together, gives me the job handle back. And then I have to send the job to the scheduler and await the results. So literally result set equals await job.exec. So this pauses your JavaScript program in your browser until the result set is complete, and then it can resume from there. And you can use that result set. It's an object which is JavaScript enumerable and iterable, so it can be cast to an array and treated like an array-like object. And in fact, what I do down here is I make an array from that result set, doing exactly what I just said. I join it together with the empty string. So now I've reconstituted my string from my individual characters that came back as my result set. And that string is now called all caps. And then I use the alert function to put it on the screen. And this is DCP in a nutshell. There's not a whole lot that's not on the screen right now that's required to run a DCP job. Of course, applications without user interfaces are useless. So let's build a user interface. That code that we just had on the previous page, I'm going to wrap that up in a function called go. And I saw the meeting controls come down. I don't know if that means somebody's trying to talk to me or not. Hope not. Okay, I'm going to wrap that other stuff on the other screen up in Go. So that was these the actual nitty-gritty parts of the work there. I'm going to attach that to a button click event that actually runs it. So in here, I'm going to declare the body of my document. So a little bit of text. Two input elements, one called input string, that's where the string that I talked about comes from. The other one is a button that causes the go function to run. I'm going to declare two text areas, and these are just for progress output. So the first one is going to receive ready state changes, and the other one is going to receive the individual results. I alluded to these a second ago. You need some events in order to really make a useful web application. So we have a few that we've exposed that you guys can use. One is called ready state change. And that just tells you what's happening to the job handle as it goes through its life cycle. So it'll tell you things like, deploying, doing this, blah, 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 deployed, completed. We have a result event that fires as the results flow back to your client application. And we have a complete event that fires when the job is complete. This is the same time as the job.exec promise resolves. I mentioned that for the benefit of folks using frameworks like React that compose better with events than with async await promises. So down here, you can see that I've got some of that code that I had up there earlier that gives me my job handle, and those events, we attach them with job.on ready state change. And over here, I'm just sending those events into the one text area, and I'm sending the strings from those events into the other text area. Let's put it all together. This is actually a complete DCP web application, not a character missing. So you can see that the basic nuts and bolts for getting something to distribute on the network is really not, a two-day operation. And when I paste the link to this slide deck into the chat at the end, I'd encourage you to save it so you can refer back to it later. This is a complete working example. Besides the code, you need a couple other things to get your jobs up and running. So you need a portal account. You get that by visiting distributed.computer. You're going to need a bank account in the portal with enough funds to deploy your job. Now, Dan talked to you about these earlier with the bank that we've got. So you can do enough work on the network to have enough credits to deploy your work. But if you sign up during the hackathon, we'll give you 25 credits. Don't look at that bottom part. It's 25 now, so that you'll be able to really do some work this weekend. Make sure you sign up and get those credits, even if you wind up not writing a DCP application for the hackathon, because you might want to write it later. So you can sign up at the portal. And then you need a couple of little things that help us identify you and your work on the network. So the first thing you need is an identity key store. And this key store helps us identify your workload on the network. My face is on top of the graphic on my Zoom. I hope it's not on yours. If it is, you can see it later when you go back through the slide deck. But when you go into the first dev section, there's a part that says your keys to DCP. There's a green plus. You can click on it, and that'll let you download. It'll create a key store for you and let it download and let you download it. And that key store contains your identity. You can revoke that key at any time. So it's actually the identity for your application. If you're doing this with Node.js, that file goes in the .dcp directory from your home directory, and it'll find it in there. If you're writing a web application, you put that id.keystore file in the same directory as your web app. If you're doing React, that's usually the public directory before you pack it up. Let's see, and you can make, recommend making that one a blank password because you can revoke that key store when you're done with it. You need one more key store though, and this one is for the people using your application. So anybody using this application is going to need some funds to make use of it. So you're going to download a bank account key store, and this is called default.keystore normally, and you can find that in the wallet tab of your portal account or the portal account of whichever user you have that's using your application. I recommend you leave that in the downloads folder of your web app, and I recommend you put a password on that and make it a good one. Anybody that has that file and your password can take your credits. So don't lose control of it, and if you do, immediately log into the portal, transfer your funds to a new account, and close the old one. So, and the reason that we have two key stores, one identifies your application to the scheduler, and the other one identifies the funds that are being used to pay for the job in our DCC unit, which measures, you know, your compute and your IO that are used. So we want the end users to pay for the work, but we want the software developers to identify themselves to the network. So let's try it out. As Dan was talking earlier, I remembered this hasn't been tested on DCP v4, so let's find out if it actually still works or not. So what I'm doing here, this is an iframe in my slide deck that actually contains exactly the application that we saw a few slides back. So this is my input string text area, and this is my button that links to the Go function. And I am being asked to supply my key store to pay for the work. And that should be right along in here. And I'm going to open that up. And along the left, wow, this is running really fast. Along the left-hand side, you can see the job going through its various states. So the most interesting one is that it got to the deployed state, which means that it is out on the network. Now we can see that we've got some results coming back on the right-hand side. And this is where the result events fire. Eventually, this will have hello TOHacks in it in all uppercase. So you'll see that there's a letter H here. That was from the first slice that came from this part of the input string, and there's the next one there, and so on and so forth. Now I know that right now we don't have very many machines on the network because almost all of our workers are still running the V3 clients. So we're updating a few hundred cores for you literally as we speak, and they'll be ready by tomorrow. So things will run a little bit faster tomorrow than they are today. And you can see now that we have work coming back, and we've got a bunch of results. And now we're just waiting for probably 1, 2, it looks like slices 3, maybe just 3 is still out there in Never Never Land somewhere. So DCP operates on a volunteer compute basis, which means that sometimes you send work to computers that go away. This can happen because somebody needs to use their machine, so they've shut it off, the power's gone out, the internet's gone out, or they might be using our worker that works as a Windows screensaver, and they sat down on their computer and hit their shift key, which kills all the work running. That's actually okay, because our scheduler will notice that after a little while, and it will resend that traffic to another worker on the network so that eventually all the work will be complete. Now, if this was V3, this would have happened already. So I'm thinking that we need to play a little bit with our resubmission timings in time for your work tomorrow. But we'll get that taken care of. New products always have interesting, fun glitches. And for something that I never tested, this worked pretty good. I'm sure that Slice 3 will come through at some point in time in the near future. So I am going to switch back to, I guess I'm going to stop my share. And I am going to take questions from the floor. Did I have to write the code to ask for the key store? DCP automatically does that. There is no code that you didn't see on that demo that was in use on my run of the demo. So that's completely buried in the background. So we have a wallet API that understands things like key stores, and it knows that if you need a password that it needs to ask you for one. So we built all those widgets in for you. I really believe in batteries included computing. And I also believe in not tying you to my batteries. So if you're in a situation where you don't want to write your own dialogues for that stuff, you can use ours, and that's great. But if you need them to match your corporate branding or to fit in with some other product, there's actually hooks in DCP client where you can substitute your own in as you would like to. And I see that we have just a couple of minutes left. Dan, are you still on the line? And oh, I guess we can't both talk at once, can we? I was going to say if you wanted to jump in and say hello to the group as well. Since each slice can run on a separate instance, can we use node libraries in the work function? The answer there is yes and no. So you can't use any node library that you want because we have very strict security on what you're allowed to do in the worker right now. You're not allowed to do any IO, and we're definitely not going to allow you to run arbitrary node libraries that dig into some of the node special stuff. So if you have node libraries that use only pure JavaScript, then yes, you can use them. And there's actually a syntax when you're making your work function. You can say job.requires and then the name of the library, I think. And what happens is our code will take that and it'll resolve it against your local module path. It'll webpack that. It'll make it available to your work function at the other end. And it'll line up the requires in your work functions to actually be able to require that stuff out of your webpack. The developer and the client both need keys right now to use the project. So the developer needs one that he leaves on the server that identifies the product. The client needs one in order to essentially identify a bank account that can pay for the work. That's being optimized in the very near future to have a more seamless experience because I don't really like making everybody deal with key store files. But the key stores are the bottom level interface. They will always work, but we're adding better stuff on top of it. Yes, you can run TensorFlow.js. I don't know how, but a lot of guys on my team have done it already, and I think there's probably a tutorial online somewhere to do it. I know we actually did quite a lot of work with TensorFlow.js a few months back. Price in terms of computing credits per core. If Dan can join, he knows that answer.
I am right here. Yes. Okay.
Dan's way better on that stuff than I am. I'm a semicolons and commas and braces kind of guy.
I'm the dollar sign and many ampersands. Anyway, okay. So with this, yeah, it's a little bit arbitrary, but we've decided to go as follows. One CPU year, and when I say CPU, you're thinking, oh, there's all kinds of CPUs. Your average typical 2.9 gigahertz CPU running for a whole year, we're arbitrarily calling that worth $100 US. And then if you divide that by the number of hours in a year, 8,760, something like that, and you multiply by 20, you end up with a compute credit, which is roughly 20 CPU hours worth about 24 cents US. But here's the thing, the more demand on the network, people will want their work to cut to the front of the line so they can slightly overbid. Likewise, the workers can under ask if they want to attract more work to them, and so on and so forth. So we're actually letting free market effects ultimately determine the cost of work on the open network, on the public network. We have stuff called private networks. So that's what we're doing at universities, where we're creating private networks on the campus, where essentially the credits more or less disappear, or they don't have any financial value. It's just deploying your own compute and so on and so forth. But on the public network, you can bid a price for the work you want done. You can also just let it do the market value, so you don't have to do anything. You know, I'll just do this at market value, and it just does it. And the workers doing all the work collect those credits. So you can see what happens. Money is flowing from the demand side to the worker side. But the workers can become the demand side if they accumulate all the credits and then they use them to deploy their own work, then it ends up being net zero. So those who do more work and aren't concerned with deploying work, they can actually cash those credits out for actual cash. The demand side, if they're needing to deploy more work, then they're actually leaving the computers participate, then they buy credits. And so really it's a sharing economy on compute power. Okay, so how's distributed approach different to that of other software like Apache software, Spark, or let's even talk about Docker containers and Kubernetes and VMs and all this crap. Okay, the biggest problem in edge computing right now is the ability to stitch together disparate operating systems, hardware platforms, different chips, different capacity, latency, like just all the different chunks of different stuff out there, stitching it together and creating a uniform or normalized compute mesh, right? So when Wes was saying earlier that DCP will, like water, run on literally anything and take advantage of every last cycle of every last type of chip run by any operating system and create consistent, uniform compute environments with which you can deploy your applications. I mean, think about that. And because it's web tech, I mean, the same web app that you could have, if you have a time machine, viewed in 1995 on Netscape looks the same in Chrome 2021. How's that for backwards and forwards compatibility? So write your application once and it will work pretty much almost forever. So these are some of the main, like all of our different, or most of our differentiators come from the fact that we're built on the web stack and all of the advantages of the web. It's ubiquitous, it runs everywhere, it's future-proof, backwards, forwards compatible. The whole world speaks web. It has some of the richest libraries and ecosystems of apps in the whole 9 yards. I mean, it has the security. I mean, we all do online banking, right? I mean, that's because billions of dollars have been put into making the main browsers or the web stack secure and have high performance. So we get all of that for free by building on the web. I don't know if, I mean, Wes, you might want to jump in on how we're different from Apache Spark specifically, but I hope I nailed the high points.
Yeah, I think you probably did. I actually don't know enough about Spark to talk intelligently about it. So differentiating it between it and us is difficult. Although if you want to actually take this offline and teach me what you know about Spark, I'd be happy to tell you how it's different from DCP. But in the interest of time, I'm going to move on.
Sorry, last good question from Kat, Wes. Is there an estimation of how much the work would cost before it is sent out? And this is actually extraordinarily useful. There's local exec to practice with your work first locally. You can also estimate it beforehand to get what the market value would be. And finally, the easiest thing is if you specifically define the price per slice. So if you say it's 1 millicredit per slice and you have 1,000 slices, well, you know it's going to be 1 credit right off the bat.
Yeah. So yeah, you can essentially, there's a couple of different ways that you can price work. One is related to market value and one is in an absolute price basis. And when you use the absolute price basis, you have absolute control over what it costs, but you don't have control over your scheduling priority. And vice versa, when you do it related to market value, you have less control over exactly what it costs you, but you have more control over where you sit within the scheduling priority or the network. So for example, if you wanted to run a job that would normally run for $1 and you're saying, well, I only want to pay 10 cents, it'll take you a while to get it back. But if you say, but I'm willing to spend $5 you'll get it back much more quickly. And similarly, if you want to run a really long job and you say, I don't care what it costs, just make it cost more than the market value so that I get it done nice and fast, we can do that as well. So there's a few different options. Now, with respect to what you'll be able to use this weekend, a lot of our costing stuff is currently not working in V4. So we're just looking at flat price per slice as a scheduling priority, and really nothing much more than that. So for most work, I just recommend leaving it at market value for the time being, and you'll get good performance right now. So I just wanted to jump back. We missed a question from Abhishek Patel, who asked about a work function calling another DCP job recursion style. So that's not directly supported at this time. What you can do is you can return the work. You can essentially send out and come back and send out and come back. So an output set can be used as an input set, but you can't sort of have them feeding each other right now. That's actually on my to-do list for the not too distant future, is to be able to have what I call streaming jobs. And at that point, we'll be able to connect the two jobs together and do that at the scheduler level, where essentially the output of one job will become the input for another. So that's very similar to recursion. We have to be careful about what can actually be authorized on the network, because we have to make sure that we have a handle on both complexity and that developers are able to express their costs correctly. But I think that most algorithms that most people would be interested in will be expressible effectively once we have our streaming workload online. And Sangam asks when to sign up to get the 25 credits. That's a really good question. Do you know, Dan?
Do you hear me right now?
Yep.
Okay. Right now, well, the specific answer is one of our team members, Eddie, is working on a tool as we speak that automates the award of credits upon portal sign up. But we know it's not ready right now, and we want it to be ready by tomorrow evening, the actual hackathon kickoff. That being said, if there's some of you who want to get to playing with DCP immediately, if you sign up to the portal and you email me your public address, actually, let me share my screen here. Oh, you'll see exactly what I'm talking about. Oops. All right, if I go to the portal, portal.distributed.computer, and I sign in, you'll see under the accounts page, I have a whole bunch here because I like creating accounts and looking at them and planning world domination. But you'll have an account. It's probably going to say default, and this is essentially, it's like your checking account. If I hit the refresh icon here, it's going to ask me for my passphrase. I'll see that I have in there a couple of compute credits. If you send me this number, specifically this number here, I'll be able to wire people some credits. I do that by hitting this, going to transfer, and I'll put your address in here, and I can wire you instantaneously some credits, just like a bank. So just sign up. I think it's like a 2-step verification, whatever, and then send me the number with your public address. Where to send this? Send this to my email, dan@kingsds.network. And I'll put that in the chat. That's for people who want to get started like immediately. I'll send you something like, I don't know, 5 credits or whatever. It's more than you need. You just need to just call your slice prices, I don't know, 1/100th of a credit, and you'll be fine. Because I think right now the most expensive slice on the network is like 0.00013 credits per slice. So you'll be fine. Hope that was helpful. Okay, so someone said, Josh said he signed up and he got the 25 credits. All right, well, then don't email me, because otherwise I'll end up wiring you extra money. Just try signing up and you should see 25 credits appear. And if you're good, if you don't, then let me know, but be honest.
Eddie is very fantastic. We have one more question, which was with respect to how I got that iframe going. Do we have time from the TOHacks people to spend 2 minutes on that? And if we do, I will answer that as soon as I finish typing here.
Yeah, sorry. Unfortunately, our next workshop starts at 7.
So that's cool. Question asker, find me on Slack, the King's DS Slack, if you need me. Alternatively, look at the source code for the slide deck that I pasted in there. It's right in there. That's just an HTML document.
Thank you so much, Dan and Wes.
Thank you for having us.
Thank you.